And so now it's my pleasure to introduce my colleague from the Czech Academy of Sciences, Nicolás Sanhueza Matamala, and I apologize, I trained to pronounce his family name only once, so I will try to invite him sometime later with better training. And Nicolás will talk about degree conditions for spanning structures in graphs. So Nicolás, please.
Okay, thank you. And everything I'm going to say today is joint work with Richard Lang, which is a postdoc in Heidelberg now. So let me first begin with Hamilton cycles, which is one spanning structure in graph. It's a classical one. So just starting from the beginning, let me say a graph is Hamiltonian if it has a cycle which uses all of the vertices. So for instance, this graph is Hamiltonian because I can find a cycle by doing this, right? Yes, so this is a Hamiltonian cycle in this graph. And the theorem which I am concerned with respect to Hamiltonian cycles in graphs is the classical Dirac theorem from 1952, which says that if you have a graph with minimum degree at least n/2, then your graph is Hamiltonian. And this n/2 here condition in the minimum degree is best possible. And is best possible, there are two ways in which this can be best possible. So two different examples, and let me recall them because they can be somewhat important later. So a graph can have large degree close to n/2 and not be Hamiltonian because you can do something like n/2 vertices in two parts. And this is not Hamiltonian because it's not even connected. So this graph, what happens here is that fails to be connected. But you can also fail in a different sense because I can have a complete bipartite graph with two parts which are very close in size, something like this. And what's the problem here? That a Hamilton cycle in a bipartite graph should be a balanced one. So it should use the same number of vertices in each part. And these two clusters don't have the same size. So here what happens, another way to put this is that Hamilton cycle should contain a matching. This is something that we know, but this graph will not contain a matching. So there's a problem of space here, which forbids this Hamilton cycle. And we will see this come later in many other situations. But okay, minimum degree n/2 gives you a Hamilton cycle and is the best possible. So how can we improve on this theorem? So we cannot decrease the minimum degree, of course. It is best possible, but there are two different ways in which we might try to improve Dirac's theorem. So maybe with the also with a minimum degree condition, maybe I can get stronger outcomes. Maybe I can try to embed another kind of spanning graphs which are not cycles, and maybe I can try to get the same result but with weaker assumptions. So we cannot decrease the minimum degree. We have already seen this, but maybe I can ask something like maybe not all of the vertices needs to have this n/2 minimum degree or something like that. So in the first part of the talk, I will kind of survey on which possible outcomes we can expect here and which kind of weaker assumptions we will work with. So let me begin first with the outcomes. So what can you embed which are not cycles? And I want to start talking about clicks. So click factors. So a click factor in a graph G is a spanning vertex disjoint collection of clicks of size kh. So every vertex is covered with a click of a given size, which is fixed and is k. So for instance, this graph over here has a triangle factor or a 3 factor. Because if I look at these orange edges, this form a triangle factor, as you can see here. And I can just similar as in Dirac result, I can ask what is the minimum degree which will ensure the existence of this click factor. So I will say this is a result in this direction. I'm just saying this is a result of Dirac type, because just as in Dirac's theorem, this is a condition of minimum degree, which ensures the existence of this spanning structure. We will see different instances of this in different order. But okay, this is the classical result of Hacknell and Semeredi. They showed also something different, but in particular, they showed this, that if your number of vertices is divisible by k, which is a necessary condition to have this k factor, and your minimum degree is at least k minus 1 times n over k, then your graph has a k click factor. And again, this is the best possible because I can select a partite graph. So for instance, for k equals 3, I can do something like this, divide the vertices in 3 parts. And again, I can make something slightly unbalanced. This cannot have a triangle factor, right? Because every triangle in this graph will use one vertex of each cluster, and the clusters don't have the same size. So this k minus 1 n over k, it's best possible. Okay, so this is a different structure, which is not a click, and you can embed in a graph. And you can try to embed something different. And so a more complicated structure is the power of a cycle, so powers of cycles. So you start from a cycle and begin to add edge to this cycle, so you get the vertices at distance at most k, right? So if this is a vertex, this vertex is at distance 0 from itself. You have vertices at distance 1, distance 2, etc. And if I want the square of a cycle, the second power of a cycle, I will have to add these edges to 0, and these edges, and these edges, and so on. And if you do this, you will get this graph over here. This is the second power of the cycle. And if I want the third power of the cycle, you will get this graph here. This is the third power of the cycle. So how are these concepts related? And there's a close relationship between the clicks and the powers of cycles, because usually the powers of cycles will contain a lot of clicks and click factors here. So in the third power of a cycle, I can find, if I look at this, parts of the graphs, actually the third power of the cycle is full with clicks of size 4. And actually, if the number of vertices is divisible by 4, you will see that essentially the k minus 1th power of the cycle will contain a k factor. So the third power contains a 4 factor, and the second power contains a 3 factor, and so on. So whatever minimum degree condition will give the power of a cycle has to be above the threshold, which gives the click factor, of course. And that is essentially the correct answer, because again, we have this result of minimum degree. This is by Komlosh, Sarkozy, Semeredi. They show that for n sufficiently large, but for every k, if you have a graph on n vertices and the same minimum degree condition, which gives you the click factor, then you have the k minus 1th power of Hamilton cycle. Okay, and if something like this happens, I will say the graph is k Hamiltonian. So it's we have this structure, which is the power of a cycle, and it has clicks of size k everywhere. And I will be concerned with this structure most of the talk, actually. But I can also have something even stronger than the power of cycle, and it's a different kind of output, because now what I desire here is not a fixed spanning graph, but a whole family of graphs. And so I will just talk only very briefly about the bandwidth condition. So I will say that a graph has a bandwidth at most b if I can order the vertices of the graph in such a way that no edge is long according to this ordering, right? So for every ij, which is an edge, the distance between I and j is at most b. And the bandwidth of the graph is the minimum possible such distance. So if I wanted to have for instance, the bandwidth of a cycle, we can see that cycles have a bandwidth which is at most 2, because I can order the vertices of a cycle to do something like this. And by doing this, no edge spans more than 2 vertices, right? So that the distance between the endpoints of every edge is at most 2. So the bandwidth of this cycle is at most 2. And this is actually true for every cycle. So in some sense, if your graph has bounded bandwidth, you can say you are bounding in some sense, the expansion properties of this graph. And if you look this graph of bounded bandwidth from far away, you will actually see almost like a line of vertices, right? So from far away, it looks like a path. And we can try to embed this graph of bounded bandwidth in graphs of a given minimum degree. And that is precisely the content of this theorem by Butcher, Chak, Taras from 2009. So what they showed here, so let me try to read this to you. So I have, apart from K, I also given a delta parameter, which is important, and is very large. And the graph H, which I want to embed, needs to satisfy 3 properties. So I will have a bounded degree, which is necessary condition. And there are some graphs with unbounded degree, which I cannot embed, even if I am given a large minimum degree. I am given a bounded chromatic number, which is also necessary because we have seen the examples consisting of k-partite graphs. They can have large minimum degree as well, but they will have bounded chromatic numbers, so I cannot embed anything which does not satisfy this chromatic number requirement. And if you have these 2 conditions and you also have this bounded bandwidth, and they need only sublinear bandwidth, not necessarily bounded, you can increase this with that, but it should be sublinear. And this minimum degree condition, which is essentially the same, which gives you the click factor and which gives you the power of cycle, except for this mu n error term, but this is as small as you like, right? So the same degree condition which gives you the power of cycles gives you this whole family of graphs: bounded degree, bounded chromatic number, and bounded bandwidth. So this is a very strong result, which if you want to strengthen the conditions from Dirac's theorem, this is one of the best things which have available now. Okay, so this finishes my small survey of outcomes. So this is some directions in which you can extend Dirac's theorem. So not only cycles we can embed click factors, powers of Hamilton cycles, graphs of sublinear bandwidth. But now let me just focus again on Hamilton cycles, but let me try to focus on how can I weaken the assumptions of the Dirac's theorem. So before I ask it that every vertex should have some kind of minimum degree, now I will try to relax these conditions. And the first theorem which is relevant in our case is Posa. So there's this theorem of Posa from 1962, and he says that if you have a graph and the vertices, you have ordered these vertices in a line like this, and you require this minimum degree condition, but the degree condition is different from each vertex. So for the ith vertex, you will require that the degree is at least the minimum between i+1 or n/2. So if I is very large meaning more than n/2, then actually this degree condition is the same as in Dirac's theorem, but for smaller vertices, for I less than n/2, this bound is required, which is much less restrictive than is in Dirac's theorem. So for instance, the first vertex should have degree 2, the third vertex should have degree 4, etc. If you satisfy this condition on the degree sequence of the graph, then the graph is Hamiltonian. And so we can do this kind of picture here. If I order the vertices using this numbering here, and you have the degrees in this axis, Dirac's theorem says that every vertex should have degree at least n over 2 to have this Hamilton cycle. But Posa says that you can actually have half of the vertices with a lower degree. The degrees should satisfy this graph over here, but the degree can be much lower than n over 2, right? So this is one way in which you can find a stronger theorem by weakening the assumption of Dirac. Let me now mention a different direction, which is actually very related to Posa conditions as well. You can have a condition which I call OR type by the theorem of OR. So if you have a graph on n vertices, and for every pair of non-adjacent vertices, the sum of the degrees is at least n, then your graph is Hamiltonian. So again, if you have Dirac's theorem, every degree should be at least n over 2, so this sum will be satisfied for every pair. But this theorem is saying that you don't need to check this condition for every pair, only for the pair of vertices which do not form an edge. So this is another possible weakening of Dirac's theorem. Let me mention two more ones. So another possible assumptions, you can have you can find Hamilton cycles in a multipartite setting. So there's this theorem by Moon and Moser from '64, and they say that if you have a balanced bipartite graph, two parts of size n, and every vertex in each part has at least n over 2 neighbors in the opposite side, then your graph is Hamiltonian. So this looks like Dirac's theorem, but note the degree, the requirement is much smaller, right? Because the global number of vertices is 2n, but you're not requiring degree n, you require degree n over 2. So in this bipartite setting, you can actually save some degree by using this theorem. And so all of these theorems are classics. They're from the 50s or 60s. Let me mention a modern type of assumption. So this is maybe more new for you. So this is deficiency assumptions for spanning graph properties. So this is a way in which you can measure how much a graph is far away from satisfying a property, in this case being Hamiltonian. So I am given a graph G, and I ask, what is the minimum t and positive integer, such that if I take the join meaning I join with a click on t vertices. So I have a click on t vertices here, I will put a click here, and I will put the complete graph, bipartite graph, between these two parts. And I ask, what is the minimum t such that this new graph is Hamiltonian? Okay, so if my original graph had n vertices and I take n to be at least n, then you get, even if G is empty, in this n G joined with Kn, you will have a Hamiltonian graph. So but if G has some edges, maybe you can save some vertices in this by using this kind of joining vertices in the graph with a complete graph. So the closer you are to being Hamiltonian, you will require this t to be smaller, and this t will be the deficiency of the graph with respect to the property of being Hamiltonian. So this was studied fairly recently in this paper by Nenadov, Sudakov, and Wagner from last year, and they found an explicit and best possible function, f and t, which I didn't want to write here because it's difficult to write. There are some case distinctions and such, but there's an explicit function. And this function says that if the graph has n vertices and the number of edges is at least this function plus 1, then this graph is Hamiltonian. Okay, so in some sense that we found this best possible number of edges, which will ensure that when you take this click on T vertices and you add this to this graph, you will become a Hamiltonian graph. So this is a different direction, and to extend this kind of theorems, and a very recent one. Okay, so now we have already said.
So Nicolás, can I have a question?
Yes.
So the previous theorem was stated only in, like, the parameter there was the number of edges. So yes. Which is usually not the parameter that you care about when you want a Hamilton cycle. So my guess is that if I asked the question about the mean degree, which is usually the more natural one, you wouldn't get anything more than just plugging it into Dirac's theorem, is it?
Probably that is the case, because for sure the extremal examples for these functions do not have a condition of minimum degree. They usually consist of a large clique and a set of isolated vertices. So yes, I don't know if you require minimum degree instead of number of edges, you will sure get a different answer. And but I am not exactly sure if it will reduce exactly to Dirac's condition. This I am not sure. Okay. Okay, let's continue. So, okay, we have seen two different directions. So stronger outcomes, so I can try to embed structures which are not Hamilton cycles. And I can have different assumptions. So instead of requiring minimum degree, I can say something about the degree condition or the number of vertices, the sum of degrees, etc. So can I actually try to combine these two kind of properties? So can I try to have clique factors under Posa-type conditions, or any combination you will like? And so let me just, it turns out that you can do this. Let me just focus on one case, which is clique factors with Posa-type conditions. So this is a result by Treglone from 2016. So he found that if you have n sufficiently large, divisible by k, which you need for k factors, and you have this sequence of vertices, and your minimum degree is this function over here, you have a k-clique factor. So this function here, so usually for to use Hagnall-Semeredi theorem, you will like the degree to be k minus 1 over k times n. So this k minus 2 over k times n is much smaller than this. But as soon as you increase this ordering of the vertices, this degree, you will get this degree sequence, and it will increase until you get to this n over k. And in that case, the bound will become this, right? So you can save some degree for some vertices, but only for the first n over k ones. So again, we can do this picture to see exactly how much degree can we save. So this is Hagnall-Semeredi, which minimum degree, which gives you the clique factor. And this result by Treglone says that you can even save some degree for the first n minus k vertices. And it's okay, I could talk the whole evening about these possible combinations, but not maybe just let me try to complete this table over here. So these are the possible structures you can find in your graph. This is Hamiltonian cycles, square of cycles, power of cycles. And here, when I wrote super Hamiltonian, I mean these all graphs with chromatic number k and bounded bandwidth. Okay, so Dirac's theorem is Dirac's condition for Hamilton cycles. And the first thing we saw was to Dirac condition, minimum degree, to embed clique factors, to embed power of Hamilton cycles, and to embed this bandwidth type of condition. And then we saw that to embed Hamilton cycles, we can use the other type of assumptions here. And here's Posa theorem, the OR theorem, etc., etc. So what else is known? So we know this Posa theorem for clique factors by Treglone, but and not much more cases are known. So as far as I know, this is the complete table. which is known so far. So this OR theorem for clique factors is a result by Kostochka and Kierstead. The multipartite result for clique factors is a result by Kivash and Mycroft. The deficiency for clique factors is a result by Fresky, High, Treglund. This is a recent one from this year. And but for squares, powers of Hamilton cycles, and these other bandwidth conditions, actually not much is known. So it actually is known only in this case of a square of Hamilton cycles. So these Posa-type conditions for squares of Hamilton cycles, which is the result over here, this is a result by Strenghten and Treglund, and for OR-type conditions for squares, this was shown by Chow. And what's interesting here maybe is that the results for squares of Hamilton cycles are always the same, which gives the corresponding clique factor. So to have a square of Hamilton cycles, you will have a lot of triangles. And the same degree condition which gives you the triangle factor gives you the square of Hamilton cycle, even in this Posa condition, in this OR condition. But not much is known, actually. The rest of the table, it was not known before this. But this is essentially our first main result, is that we can actually fill this table so we can have the best possible Posa-type condition, which gives you this power of Hamilton cycles. And we can also say the same for this OR-type condition, for this deficiency condition, etc. And our proof will also work in this stronger setting where we don't only want this power of Hamilton cycles, but we want this stronger setting where we can embed this whole family of graphs, right? So bounded chromatic number, bounded degree, and sublinear bandwidth. Our proof will also say something in this direction. And let me just say here that the same thing that happened for the square of Hamilton cycles will also happen here, that the condition to get this power of Hamilton cycle, to get the K power of Hamilton cycle, sorry, the K minus 1 power of Hamilton cycle, you will need a K factor. So the same condition which gives you the clique factor is the same condition will give you the power of Hamilton cycle. So essentially what we can show is that every time you have the clique factor, you already have the power of Hamilton cycle and you already have the corresponding bandwidth graph condition. Okay, is the statement kind of clear? And so let me focus on one particular case, which was this Posa conditions for powers of Hamilton cycles. So this is one thing we show. You have a graph on n vertices, and you have this degree sequence of graphs, and you have this minimum degree conditions. So this formula here was the same as the Posa-type condition for clique factors. But we say that as soon as you have this condition for clique factors, then you also have this power of Hamilton cycle. And you have this error term here of mu n, which maybe you don't like, but let me just say that this mu n actually cannot be completely removed. You cannot replace it by a constant, but you also can replace it by something which is sub square root of n. So in some sense, you need an extra error term here. And yeah, so let me just say that this answers some conjecture. So this was conjectured by Strenghten and Treglund and asked by Balog, Kostochka, Treglund. This particular case of a Posa-type conditions for powers of Hamilton cycles. And so I want to say something about the approach we have. So actually the approach to prove all of these results, even the Posa or type conditions, etc., is actually the same. So we prove, actually we reduce the property of giving K Hamiltonian, so having this K minus 1 power Hamilton cycle. And we reduce this property to some set of abstract properties, and I will tell you in a minute what do we mean by this. And we will show later that these structural assumptions of Posa condition or condition, etc., will lead to these properties. So the proof will be reduced to check that these properties are satisfied. So let me say something about what these properties R. So we call this Hamilton frameworks, and Hamilton framework is a structure which, if you have this structure in a graph, you will have this power of Hamilton cycle essentially. So let me say just a few obvious things. If you have a Hamiltonian graph which is non-bipartite, then your graph is connected. Well, of course, it should be connected. You have a Hamilton cycle. Your graph should have an almost perfect matching. And this is again true because if you have a Hamilton cycle in your graph, then you can select these edges in an alternating fashion. And you will cover everything except maybe one vertex, but this is an almost perfect matching. So you have a large matching. And such a graph should also have an odd cycle. And of course, because I want this graph to be non-bipartite. Okay, so I didn't say anything interesting here. But let me say a graph which satisfies those properties is a Hamilton framework. And maybe one could ask the converse of this. So if you have a graph which is a Hamilton framework, should it be Hamiltonian? The answer is clearly no. And there are some examples you can think of. I can draw one here. This is a graph which is connected, has a perfect matching actually, and has odd cycles, but this is clearly not Hamiltonian. But actually, if you ask if this is a Hamilton framework or not, but I can destroy the property of being a Hamilton framework very easily. So this is not a very robust Hamilton framework. If I happen to delete this edge here, I will actually destroy connectivity from this graph, which I don't want. And if I delete some vertices or I delete one edge, I can destroy the matching, I can destroy, etc. So actually, I not only want a Hamilton framework, but I want a graph which is robust. It has these properties in a very robust way. So robust against deletions. So again, this is the definition of Hamilton framework, connected matching cycle. And I will say a graph is a mu robust Hamilton framework if I delete at most mu n vertices. So I am allowed to delete this number of vertices, and I am allowed to delete this number of edges at every vertex. So I can even delete edges which touch every vertex, but the deleted edges should not have a very large degree at any vertex. And if after these deletions, I am still a Hamilton framework, I will say this is a mu robust Hamilton framework. So the graph is connected, but it's not only connected, it's connected in a very robust sense. It's robust against these deletions and has the matching robustly against deletions and etc. So one lemma which you can show, and that's something that we also use in our paper, is that for every mu, if you have a sufficiently large Hamilton framework, which is mu robust, then this graph is Hamiltonian. And it's actually not that difficult to prove. You can reduce this to some kind of regularity type proof if you like. But what we are actually interested here is how to extend this property of Hamiltonicity, Hamilton cycles in graphs, and to this stronger kind of things which we want to embed, which are not just Hamilton cycles, but powers of Hamilton cycles. And we will actually have a detour from graphs to hypergraphs, because it's actually easier for us to state our results in terms of hypergraphs. So let me say a little about hypergraphs. So a hypergraph is a K-uniform if every edge has size K. And a walk in a uniform hypergraph is a sequence of edges, and every two consecutive edges will intersect in exactly K-1 vertices. So this drawing over here shows a walk. So this sequence of edges which are appearing there intersect in two vertices. Each pair of consecutive edges intersect in two vertices. So this will form a walk in a 3 uniform hypergraph. So I am interested in defining walks because by using walks, I can define a concept of connectivity in hypergraphs. So actually I will say that a hypergraph is tightly connected if between every pair of edges, I can find a walk which begins in the first edge and ends in the second edge. And this hypergraph, which you can see here, is actually a tightly connected one, which maybe you can check. So we are interested in this concept of connectivity for hypergraphs because it will allow us to say something about powers of cycles in graphs. And this is the main reason why we are allowed to say this. This is the connection. So if I am given a graph, I can define the k-click hypergraph, which I denote G to the K, is a k-uniform hypergraph. And the edges of this hypergraph are going to be the k-clicks of G. So for instance, it's a 3-click hypergraph. Every triangle in the graph will become an edge of size 3 in this auxiliary hypergraph. And why this is useful to us? Because we are interested in powers of cycles. And if your original graph is the k-1 power of a cycle, then this auxiliary hypergraph, this click hypergraph, will be a tight cycle. So this is a square of a cycle. And if I look at the 3-click hypergraph, you will get this structure here, which is a tight cycle in hypergraph. And this is a structure which we know something about these things. There are a lot of results where you can know for conditions, which gives you tight cycle in hypergraphs. This is a structure which we know how to work with this. So we will actually look for tight cycles in these associated hypergraphs. And again, so let me say some obvious things. A tight cycle is actually a tightly connected graph. This is something you can try to check easily. If I have an edge like this, I can just follow the edges in this order. You can find a walk between any pair of two edges. And something that is also true is that a graph, which is a tight cycle, contains a very good matching. And you can actually find a perfect fractional matching in this tight cycle. So a fractional matching here is an assignment of weight to the edges of the graph, and every vertex should receive the same weight. And this is just because in this tight cycle, every vertex is in the same number of edges. In this case, 3, in general, k. So if you can assign the weight 1/k to every edge, you will have defined a fractional matching. So this is similar to what we have seen in the case of Hamilton cycles in graphs. So cycles are connected, contain a matching. And here we are saying something similar. So maybe we can try to reduce the property of containing a tight cycle to these two properties. And so this is what we can deduce. If your graph has this k-1 power of a Hamilton cycle, then this auxiliary hypergraph J to the K has a tightly connected subgraph H, which has a perfect fractional matching. So this connected subgraph H is the subgraph which contains the given tight cycle, right? And here's some difference between this case and the graph case, which maybe is good to emphasize. Get connected. Even if you have this power of Hamilton cycle, and this is a difference between this setting and the setting of Hamilton cycles, right? Because as soon as you have a Hamilton cycle, you are connected. But if you have this tight cycle in a hypergraph, doesn't mean the edges are tightly connected. You have a spanning, tightly connected component, but you can have some edges which you cannot reach from this cycle. And in this case, it will be important for us to make this distinction. Okay, but we have this. So we're going to try to emulate what we did before. So let me define, before we define Hamilton frameworks as a graph which satisfies some of the conditions which you get when you have a Hamilton cycle. So a Hamilton framework would actually be a pair, so a graph and a hypergraph. The hypergraph will be a subgraph of this auxiliary hypergraph. What I will like from this hypergraph is that the hypergraph is tightly connected. I will like this hypergraph to have this matching. And for technical reasons, I will also require, before we asked for this odd cycle here, let me ask for a cycle which the length is needs to be co-primed with K. We did this for technical reasons, but I will mention later some ways in which can actually get rid of this cycle. But we have these three conditions which define a Hamilton framework. And as before, maybe we don't only want these conditions, but we want these conditions to be robust. So I will say this framework is actually a robust framework if I am allowed to delete mu n vertices from G, and I am allowed to delete edges from G as well. And after you do these deletions, what remains is still a K Hamilton framework. So in these deletions, you delete vertices and edges from G, and you should also be deleting clicks from H, and you will delete an edge if you have deleted one vertex or one of its edges, right? But if after every deletion you are still a Hamilton framework, we will say that you are a mu robust Hamilton framework. So our result is actually that if you have any mu and every sufficiently large Hamilton framework, which is mu robust, then in G you can find this required Hamilton power of Hamilton cycle, which is equivalent to finding this tight cycle in this hypergraph H. So this is actually our main result, because this result, which I showed you before for the Posa or etc. type conditions, are actually all deduced from this theorem. This is the only thing we prove, and then we deduce the other ones. So a few words about this theorem. So the proof is technical. It relies on absorption. It relies on regularity, but and at some, yeah, let me not say much about this proof. But it's also, if you understand regularity and absorption, it's not that ugly, I think. Let me just say that this will imply all of the applications we mentioned before. And let me say that the definition of framework, which I showed to you, is actually slightly more complicated, but thanks to this, we can actually deal with other situations where we maybe don't have this cycle of this correct length, or maybe we can embed even something stronger in this situation. So we have some different type of framework which we can adapt for the Spartite setting. So maybe you have a K-partite graph and you want to find powers of cycles or embed this bounded bandwidth graph. And in this partite setting, you will not have this cycle of the given required length, but we can adapt our frameworks to work in this setting. And we can actually do some other adaptation to embed something which is slightly more complicated. So in the bandwidth setting, you can actually embed not only K colorable graphs, but you can actually embed K+1 colorable graphs if you are given that one of the colors is only used very few times. This is something that is also present in the original bandwidth theorem. So for instance, if you want to embed a Hamilton cycle on an odd number of vertices, this is not 2 colorable, it is 3 colorable, but what you can use one color only once. So we allow, there's some setting which we can allow K+1 colorable graphs, provided one color is not used many times. So this was known for this minimum degree condition, and we can also say something in this direction for this more general situations, but we have to use a slightly stronger definition of framework. So this is maybe our main technical result, and all of the other applications follow from this. Let me sketch how you will use this result to derive, for instance, the Posa-type result. So by using our technique, if you want to show this graph is K-Hamiltonian, let me just focus on parallel Hamilton cycles here. So to show that a graph is K-Hamiltonian, then you can show, okay, maybe this tuple of G and all of the clicks of G, they form a mu robust Hamilton framework. And let me remind you, you need to check tightly connected, you need to check the matching, you need to check this cycle. And after you have checked this, okay, this tuple is a mu robust Hamilton framework, and essentially you are done. As soon as you check this condition, we can find the power of Hamilton cycle for you. So, for instance, in this Posa-type condition, this as soon as you are given this technical lemma, the proof is quite short. So, this Posa-type condition, I need to check if I were to prove that I have power of Hamilton cycles. So, I am given the graph, I am given the clicks of this graph, and I want to show that this is a robust Hamilton framework. So, I will have to verify this is a robust Hamilton framework. I need to check the connectivity, the matching, and the cycle. So the connectivity is given by this lemma. So we can show that when you have a graph satisfying this degree condition of the Posa theorem for k clicks, then this graph is tightly connected. And let me just say that we have to prove this lemma to apply our result, but let me just say that the proof of this lemma is actually very simple. So we can actually prove this for every n. So we don't do anything by regularity or anything fancy. This is an easy proof. We actually don't have this error term here. This is a nice proof. It's by induction on K or something like that. It's a simple proof. This will show the connectivity. And we also need this matching. But the matching will be given by this result of Strenghten. He found this factor with clicks, which in the hypergraph setting will correspond to a matching. So actually the matching comes for free. And the cycle will also is easy. We actually can get a click of this size, so there's no problem. So given our technical result, the only thing we have to show is this, and this has an easy proof. And the other settings of this OR type condition, deficiency, etc., the proof are slightly more complicated, but they're also essentially reduced to checking this connectivity condition. The click will be given by this result from other people. So this is a nice aspect of our proof. We have this technical condition, but when to check this technical condition, it's actually simple in most of the applications. And yes, I'm almost finishing here. And let me mention some questions. There are some settings where we are also interested in finding powers of Hamilton cycles where we don't know if our framework applies or not. So if you know about degree conditions for Hamilton cycles, you might be wondering about these type conditions. And this is also a very old and well-known condition, which gives Hamilton cycles in graphs. So the condition says that if you have a graph, you have the degree sequence of this graph, so the degree of the vertices ordered increasingly. And Vattel says you can have this condition for the ith vertex. So this is the same as in the Posa-type condition, but maybe you don't satisfy this condition for the ith vertex. If you don't, then you need to compensate this in the n-i vertex. So in a picture, it will look something like this. This will look like the Posa condition. Maybe at the ith step you fail, you will need to compensate this later. Something like this. And this is a well-known condition for Hamilton cycles in graphs. You might as well ask, can you turn this into a theorem for click factors, power of Hamilton cycles, etc.? And the thing is that we are actually not sure what will be the correct condition to ask to get, let's say, click factors or triangle factors. So this is something we conjecture. We believe this could be true, that if you have a graph on n vertices and your degree sequence does something like this. So this is a condition on the ith vertex, which is actually the same one for the Posa-type condition for click factors. And if you fail to satisfy this at the ith vertex, maybe you have this condition at this vertex in the 2n/3 minus I. Okay. If you have this condition, maybe you have this square of Hamilton cycle. But let me just mention that the obstacle to prove this conjecture will be only to find the triangle factor. if with this condition you can find the triangle factor, then our framework will apply. You will get this connectivity, you will get everything essentially. So the only obstacle here is that we don't know how to find this triangle factor. But actually, we're not really sure if this is the correct condition to ask. We know this condition will work for our framework, but we don't know if this, maybe there's something better here. And there's also a different type of condition. This is an interesting one because it also fails in our framework. But here what fails is not the factor, but what fails is the connectivity. We don't know if connectivity holds. So this is a theorem we have with Alan Lowe. We say that if you have a balanced k-partite graph, clusters of the same size, let's say here I have 4 clusters, and here I have a conditional minimum degree. So I have k clusters, in this case, k equals 4, and every vertex has degree at least k minus 3/2n. In this case, what it means that for every vertex x, I will look, I don't know, maybe I can look at all of these clusters, and I can look at half of the other one. This is essentially the degree condition you have. But you can have this minimum degree over all the graph however you like. What we showed is that if you have this degree condition in a partite graph, then you have a factor with cliques. And this is a factor which contains one vertex in each one of the given clusters. We could also ask if this condition not only gives you this k factor, maybe it gives you a power of Hamilton cycle, but actually we don't know how to prove connectivity. We don't know if you look at this hypergraph, which is formed by these cliques, we don't know if they're connected or not. So if they were connected, we could apply our framework, but actually we don't know how to do it. So this is interesting because it's a different direction where the obstacle is a different one. We have the clique factor, we don't know how to prove connectivity. And this is all I wanted to say. So thank you very much.
Okay, thank you, Nicolás, for the beautiful talk. Could I ask people to unmute themselves if they want? Give a round of applause.
Thank you.
So are there any questions now? So one question I had is, and I'm not sure how much is done in this setting, in the original setting of these graphs with small bandwidth, but for graph tilings, there is this notion of critical chromatic number, which somehow is somewhat related to what you said, that if there is just, the last color class is small, then it essentially doesn't matter. So if you could just recall whether anything like that existed in the bandwidth, in the small bandwidth setting, and if you could do anything about that.
Yes, I am not sure. So we can do this case where you have k+1 colors, but the one color class is tiny. And in general, I don't know. I don't know if something like this is known even in the minimum degree setting. So if I just asked about, so maybe the minimum degree, which can give you an H tiling, can you find another kind of spanning structure which looks like this? I don't know if there's any result in this direction. I don't think so. But to embed this whole class of k colorable graphs, then you are stuck with this k-1/k, because this will also allow you to embed this clique factor, power of cycles. So you can really improve on that. But I don't know if there's something in between. Yeah, I don't know.
Right. Okay. And again, it might be quite easy to get it, because what you do is you sort of combine these black boxes, one of which is the Heinal-Semerelli theorem, and that essentially exists for these unbalanced or graphs. But okay, yes. I don't know details. Yeah. So if you have a question, are there any more questions?
Yeah, Nicholas, I had a question.
Yes.
In the graph case, how, the notion of a robust Hamilton framework,
Yes.
how does that relate to, robust, being a robust expander, as defined by, the Kunos, this.
Right. So, yes, I'm not exactly sure it will be related to that notion, because you don't really have to be an expander of some sort to have these Hamilton cycles, right? So, so to have this new robust properties as we defined it, I don't know, maybe you have a path, let's say on 5 vertices, and blow it up by you blow up every vertex by the same number, or maybe you can have a path on 1,000 vertices or so. So maybe this doesn't look like an expander in this robust expander of Kunostus. I don't know, but it will be a mu robust in our setting.
I see.
So yes, I don't know. We didn't really think about that, but I don't think one implies the other, so I don't think that's the case.
Okay, yeah, I guess I was wondering if somehow your condition implied, so say like a robust expander has a Hamiltonian cycle. Well, maybe your condition implies that. Well, anyway, yeah. I mean,
so I am not sure, but I don't think it will.
But I see. Okay. Well, maybe perhaps being a robust expander implies that you have a robust Hamilton framework, or
probably, yeah.
I see. And also, I wondered if you guys considered any extension of your results to digraphs.
Yes, no, we did not.
I see.
Did not.
Because I mean, there are some kind of more basic problems that are still open in the digraph setting, like powers of cycles and digraphs, for instance. There's not even minimum degree conditions for those sorts of things. So
yes. Yeah, no, we did not check those cases.
Yeah. Okay. Well, yeah, anyway, that's something.
Okay, thank you.
Yeah.
Okay, so thanks again, Nicolás. We will, let me just remind you that next week we will have, not the last session, but one before last, we will have Rafael Juster talking also about Hamilton cycles. And the week after we will have David Correa. And then there will be 2 months of summer break. So we will then see how the situation will be in September, and we don't have any plans really. So I guess I will see some of you next week on the seminar by Rafael Juster. So thanks, Nicolás. That was a great talk and an impressive table.
So concerning your question regarding the critical chromatic number, I think it's not true for bandwidth type questions, or at least the critical chromatic number is not a crucial notion anymore. So I think even, are you not one of the authors? So with Peter and where you looked at tight paths of length, let's say n-half? Not tight, like second square
yes,
of a path.
Only that power we do. Yes, I think I'm an author of that. Yes.
Yeah, right. So, and if you think of that graph as like half the path, half isolated vertices, you can do quite a lot with the critical chromatic number. You have quite a lot of freedom. However, this is not a correct answer to the question. So the critical chromatic doesn't give you the right, well, possibly n-half is not the right thing, but for some length, it doesn't give you the right threshold. Because you show that there are actually other obstacles.
So, right, I mean, as Nicolás said, right, it should be a combination of a connectivity obstacle and some KK tiling, and right,
Yeah, okay, there's some connectivity problems. Yeah, but I'm just saying it's not, you can't just take the critical chromatic number lower bound and then prove a bandwidth theorem for, instead of the F factors what Derek and Daniela had for a really bandwidth thing with the same critical chromatic number.
Okay, yes.